We're now going to look at using Apex to analyze the illumination distribution through a series of different light pipes. The first one we're going to start with is a very simple design, a circular cross-section, linear section of light pipe. And what we can see is the rays on the inside of the pipe. They're entering the pipe, and as you can see, the total internal reflections are being used to send the light forward through the pipe. There are also going to be Fresnel reflections that will send some of the light backwards towards the input face. There are also Fresnel reflections of the light initially incident on the input face. But fundamentally, you'll see that most of the light, most of the rays, if you will, exit out at this output face. We can move the pipe around and you can see that you don't see any arrows coming from the body of the pipe, which means there's little, if any, light being lost through the faces of the pipe, which is exactly what we would expect for a straight pipe section. Now what we'll do is take a look at what the output distribution looks like at the output face, and we'll start by looking at the irradiance distribution. And what we've got here is a simple averaging of the data at the output face, and this is showing the energy as a function of area across that output face. And you'll notice that there is non-uniformity in the distribution from this pipe. We can also look at it in direction cosine space, so we'll get information about the angular distribution of the light. And what we see is on a plus or minus 1 scale, we do have light coming out at all angles, but again, it's reasonably uniform, but not completely uniform. One thing we might want to do now is to compare the output of a square section of pipe to that from a circular section of pipe. Again, no rays being lost through the sides. Most of the energy is exiting from the output face, as expected. And let's take a look at, again, both the irradiance, the energy per area plot, as well as the intensity, or the information in direction cosine space. And you'll notice that our energy distribution is a bit more uniform for the square cross-section than it was for the circular cross-section, so let's take a look at them. And in both cases, we've applied a simple adjacent pixel averaging to take care of statistical type noise or shot noise. And here is the intensity distribution in direction cosine space for the square pipe, and again we can compare that to the circular pipe. But we can see that we get a different distribution of energy for the square pipe than we do for the circular pipe, although the amount of energy exiting out for each pipe is very similar. These are two simple classical examples of light pipes that are used to send light from one location to another in a method that is as lossless as possible. Unfortunately, it is not always possible to send light through a light pipe without losses. Also, there are other times where we deliberately want to introduce loss into a light pipe, something that's often referred to as frustrated TIR, where we set up the pipe in such a way that light will deliberately be forced to exit the pipe. And one way of doing that is to create a tapered pipe. And in this case, it's very clear to see that rays are not only exiting out the output face, but they're also exiting out the top, the bottom, and both sides. So what we might want to do is to take a look at the light exiting for what I'm calling the top face. And we've already done this calculation. So here's what that output distribution would look like, again with our applying a simple averaging. As the light first enters the pipe, no matter what its angle is, it is going to, for a short distance, all totally internally reflect and bounce forward down the pipe. However, as the light tapers, there are going to be some of those rays that are incident on the surface at less than the critical angle, and those rays can simply exit out of the pipe. And as we propagate a further and further distance, we see more and more of the light exits via this frustrated TIR. And what this allows us to do is to illuminate devices or areas all along this path of the light pipe, not simply illuminate the area at the output face of the light pipe. But there is still quite a bit of light exiting this light pipe. It's a very short section, and to take a look at this information, This is showing what the distribution of energy is at the output face. And indeed, this is most of the energy, so we could easily illuminate an area using the output face of the pipe or extend the pipe further to send light into a different region. The purpose of this was simply to show you how you can use Apex to analyze the light leakage through your tapered light pipe or any light pipe section. The last case we want to look at is the case of a bent pipe. What we can see is, again, a lot of light exiting out the output face. Due to Fresnel reflections, we also have light exiting from the input face, lost at the input face. And in the square sections, we have very little light lost, if any. But let me zoom in on the bend itself. Okay. In the area of the bend, you'll notice that we see some of the light exiting. Because of this bend, and 90 degree is a rather excessive bend, we see quite a few arrows leaving the pipe. This simply means light is leaking out. But you'll notice you see most of the arrows on this lower face of the pipe and few, if any, on this inner face of the pipe. What this allows you to do is to analyze where the losses occur to determine the right locations to put any mounting or other types of mechanical hardware. But of course, we also want to take a look at what the light distribution is and how much light is lost in the different locations. And so let's take a look at the light that is output at the bend. And as you noticed when we were looking at the rays, most of the energy seemed to be lost near the beginning and the end of the bend and just a little across the base of the bend itself. We can also then look at the irradiance distribution at the output face. And this is looking at the raw data. We can also select the option to average, in this case just an average over the adjacent pixels. Click on OK, and then just come up here to my menu and select to do another picture plot. So this is the raw data, and this is the result of a simple averaging. So we have a nice uniform distribution of energy coming out of the output face of our light pipe. So what we've looked at here are several simple examples of light pipes, but they are very realistic models for light pipes. We've also looked at the capability of Apex in analyzing what the energy distribution is and how to use Apex to determine where you're seeing losses from within your light pipes. Apex can be used to look at these simple, realistic models or any type of complex light pipe structure you need for your illumination design.